the atomic theory. We have a few rules that go into the atomic theory that we accept as true. You guys remember the difference between a theory and a law? What does a theory do? A theory attempts to explain, where a law just basically states what is. We accept them as being relative truth in science, though. So don't discount it because it has the word theory in it. It means it's well substantiated if it's being called a theory. All right, the first rule here is that each element is composed of mostly indestructible particles. I added the word mostly in there because we do know that we can break apart atoms with atomic chemistry, radiochemistry, things of that nature. We're not going to be exploring that at all in this course. So just in this course, think of an atom being as small as possible. Small, indestructible particles that are extremely small. A second rule here are all atoms of a given element have unique properties. So for example, if you're taking a look at a sulfur atom, there is nothing else in the universe that is exactly like sulfur. There are things that are similar, but nothing else is sulfur. Only sulfur is sulfur. Or that atoms form in whole number ratios to form compounds. Keep in mind, in chemistry, we like to use the words compounds or molecule interchangeably. So if you ever hear me say the word compound, I may also be referring to a molecule. These words essentially mean the same thing. All right, so let's go ahead and take a look at a simple formula. I've drawn it a couple times for you guys. So we have water. And we have this type of format. Notice the way I wrote the 2 there. I wrote the 2 as a subscript. And this is immediately following a hydrogen atom. So that means that we have 2 hydrogen atoms and 1 oxygen atom, and when that all combines, that is a water molecule. So we like to use the little subscripts here to denote how many there are. If there is no subscript written there, it's assumed to be 1. Another thing that we're going to see probably chapter 6 or so, I'm just going to show it to you here now. If we write something like this with a 2 in front, that means that we have 2 of the molecule. So this means 2 water molecules or 2 moles of water. So here we have the 2 in front, 2 moles or molecules. Probably haven't heard the word mole yet. We haven't used it yet in this course, but it essentially is a chemistry unit for mass, essentially. It is often useful to illustrate how science works by looking at older models. So these models of the atom used to be a very predominant one until it was disproven. And this is called the so-called plum pudding model. And I know, in the US we don't really have plum pudding here. You can think of it essentially as like a fruit cake. So basically here, or we can have like a blueberry muffin or something. So here we have a sea of positive charges. You can think of that as being the bread. And then we have our little fruit pieces, our berries in there, which are our negatives. So there was a very classic experiment that disproved this, and this is the so-called gold foil experiment, Rutherford's gold foil experiment. You need to be familiar with this. This stuff tends to crop up in the homework. You may see questions about it. So one thing that Rutherford did here was he had alpha particles coming out of this here. Alpha particles are essentially positive charges. And one thing that scientists knew well ahead of time, prior to this experiment, are how different charges react with each other, how they interact with each other. So we call these electrostatic attraction or repulsion. So for example, if you have like charges, you guys know how these interact? So if we have two positives coming next to each other, what are they going to do? Are they going to attract to each other, or are they going to repel each other? They tend to repel each other. So we say that like charges repel. So these are going to push away from each other. And then same deal, if you have negative charges coming together, these are going to push away from each other as well. And then if we have opposite charges, these tend to attract. Positive and a negative, these are going to push towards each other. What led Rutherford to change his opinion on the at the time accepted model of the Plum pudding model was the scattering pattern that he saw with the alpha particles. So he's shooting positive charges towards a little thin foil of gold, and then he saw that most of them passed through, but a significant portion were either bounced back towards him or in relative scattered directions. So let's take a look at the comparison. If it were the Thompson model, meaning the Plum pudding model, most of the particles should have just passed through because they're effectively just kind of averaging the charge out. They're not being attracted or repelled by anything. They're just kind of all passed through. And the Rutherford model, which is actually the currently accepted model, he noticed that you're having some reflection here. And what this tells us is that most of the positive charges are being condensed, but you still have large empty space. And he also discovered that there is large empty space. So once again, if this is what he expected to see, where you did have a little bit of scattering, but for the most part all of it passed through straight, but he found that you did have some reflection, some deflection of the particles, but most of it still passed through. So now we have the currently accepted model of the atom. So here we have a carbon atom. Essentially in the center we have our positive charges condensed into a core. Do you guys know what we call that? That's the nucleus. So here in the core we have the nucleus. And then around the outside we have our electron cloud. In general, we consider protons to be positive. Neutrons are neutral, as their name suggests, and electrons are negative. You may notice as we progress in this class, I will tend to write electrons as lowercase e minus. That's actually a pretty standard convention for talking about electrons. Alright, so what's the deal here? Didn't I just say that like charges repel? So notice here we have a bunch of positive charges here held together. What's allowing that to happen are your neutrons. You can think of neutrons as being somewhat of a atomic glue that hold all these positive charges together. There is a lot of energy associated with that. That's why when you have nuclear reaction that generates so much energy. So for example, when uranium reacts and the core breaks apart, it releases a ton of energy and leads to things that power plants or make nuclear bombs. And they're actually using a very small amount of uranium, but the reason why it's so explosive is because of how much energy is holding these together. Alright, I do want to mention here that we do have different energy levels. We'll go over that in more detail in chapter 9, I think it was, remember off the top of my head. But there are distinct energy levels for the electrons, but for now I want you guys to just be aware that there is a nucleus, core, where your protons and neutrons reside, and then your electron cloud on the outside. This here is a gross oversimplification on what it actually looks like, and I think something like this would be a little bit more accurate on how it's represented. Essentially what's happening here is that these electrons are moving so fast that you can imagine them being in the cloud because they're moving so fast. So the analogy you can think of is imagine you're trying to take a picture of a kid running in a park and you have a slow shutter speed. How are they going to look in your camera? It's going to be a blur, right? That's pretty much what's happening with the electrons. They're moving so fast that they're a blur, so we look at the general shape they make rather than their actual individual location. So here we have the results of the gold foil experiment. All right, and I'm just going to summarize what I just said. Number one is that most of the atom's mass is contained in the center in a dense core. And we refer to that core as being the nucleus. And recall that these are protons plus neutrons that are in the core. Most of the atom's volume is empty space, and that is where the electrons reside. Alright, and then one little thing I want to add to this is that if you have a neutral atom, meaning no overall charge, it works out where the number of protons equals the number of electrons. So basically, the total positive equals the total negative. They cancel each other out. Alright, so now we're going to go ahead and take a look at how we define elements. So does anybody know how we define our elements? What do we use to determine that a carbon is a carbon or that a sulfur is a sulfur? Well, it has something to do with the weight. So based on what I just said, where does most of the weight come from? The nucleus. The atomic number? Yep. And what is the atomic number directly associated with? Number of protons, yes. So we define how an element is defined here by the number of protons. Also want to mention here that the number of protons is typically also referred to as the atomic number. And we like to give this the letter Z for short. Alright, so on the periodic table that I gave you guys, each of the elements is numbered in the upper left corner. And any periodic table you look at will have these numbers on there. And basically what that number is telling me is that's how many protons that particular element has. So for example, if I had a cluster of atoms and they all had 6 protons in the core, they are all carbon. If there's one oddball in the group that has 7, that is not carbon, what is it? It's nitrogen in that case. So it doesn't matter what else is going on, the number of protons that's how we define what element it is. So taking a look here, we have some chemical symbols and how to write them. So chemical or element. The way we write this is there's typically a 1 or 2 letter designation. And you need to make sure that if it's a 1 letter designation, do write the letter capital. If it's a 2 letter designation, you must write 1 capital, 1 lowercase. This does make a difference. For example, if I had, I think I mentioned this to you guys before, if I had those 2 things, this first one here is carbon monoxide, and since you guys have periodic tables now, what is this one? So make sure you're very clear on your capital and lowercase. I do want to point out this particular periodic table has some 3-letter designations here. Does anybody know why they're like that? Yeah, pretty much almost this whole entire row here is all synthetically made. This table is actually a little bit out of date. These elements actually just recently got names associated with them. And these literally are saying 113, 114. If you actually break down what the name is saying. So if you take a look at this one here, 112, it says by. That means 112, literally. And that's what all these are doing. They're just placeholder names. So typically we don't think of elements having 3 letters. These were just placeholder names. They now have real names. And there's actually a whole list of criteria where people are allowed to name elements from. Here we have what's the so-called periodic law. Turns out back in the olden days, Mendeleev was arranging chemicals by mass on a little table that he generated here. And what he was finding when he arranged things by mass, that periodically certain chemical and physical properties would repeat. And we actually find that on the periodic table. We have since changed the structure a little bit, making it a little bit easier to read than Mendeleev's table was, but he essentially found that particular groupings of elements had similar properties. When elements are arranged in order by mass, certain properties, whether they're chemical or physical, recur periodically. That's actually where the name, the periodic table of elements, comes from. So in general, the way you want to look at this table is elements in the same column get these group numbers. It turns out everything in a particular column has similar chemical and physical properties. All right, and there are certain groupings that I want you guys to be familiar with. And I'm going to go ahead and label them on here. So I'm going to write on the table here. I recommend you write on your table as well. These are the alkali metals. The alkali metals. And the next ones are called the alkali earth metals. From soil, essentially. All right, the next group here that I want you to be familiar with is this one here in the transition metal area. This group right here starts with copper. These are often referred to as the precious metals. So there we have copper, silver, and gold. So I want you guys to be aware of this here too, that we have different names on there. It turns out that elements that were discovered a very long time ago, many of them have old, their symbol comes from old names. So we had cuprium, I forgot what the other two were, but they have different symbols than what they might seem to have. So copper is not Co, that's cobalt. Copper is Cu, silver is Ag, and gold is Au. All right, the next set of groups, there's two more that I want you guys to be familiar with. To keep in mind that every single column has a name. All right, the next one I want you guys to be familiar with is this group, group 7. When I refer to group numbers, I'm going to use the Roman numeral numbers that are there. So there I'm using the 7 as the group number. These are the halogens. You guys may have heard of a halogen lamp before. They're like the little neon signs. They typically contain one of those elements in there to get them their color. All right, and then the last one here, does anybody know what that one's called? The last group there? They're the noble gases, yes. They are the cool kid. Everybody wants to be like the noble gases. That's actually what drives a lot of chemistry, is that a lot of elements are trying to make themselves be similar to a noble gas. All right, so next we have the main group elements and the transition metals. So if you are looking in the last two here, so we have these two, and then we have these 6 rows here, columns rather. So if we're looking at all of that, these are the main group elements. Once again, what I'm referring to for the main group elements are the first 2 columns, and we skip across the last 6 here. So if you take a look at element 57, lanthanum, and you take a look at the element next door, and compare that to what's happening up above here. Look at the numbers. Is there a difference in how the number changes? So look at this one here. It's going 21 to 22. And then here it's going from 57 to 72. A little bit different, aren't they? It turns out that the way you read the table, if you're going left to right in this row, is after 57, it actually goes to here. And the same thing happens in the next row as well. So 89 to 104, the in-between are these. So these 2 groups actually belong in that part of the table. And because of that, we call these the inner transition. So honestly, the only reason why those are pulled to the bottom rather than inserted in there like they should be is so they fit on a sheet of paper. Otherwise, it would be a really long sheet of paper, kind of awkward. You have a lot of empty space there. So we're just utilizing our real estate on our piece of paper here by pulling this out. Just keep in mind that when you're interpreting things off the table, they technically belong inside here. And that'll come up later when we start doing electron configuration discussions. All right, there are some other main categories that I want you to be familiar with. You may notice this line right here. There is a staircase line that goes down starting at boron. That is the separation between metals and nonmetals. So on the right side of the line, these are nonmetals. If they are on the left side of that line, we call these metals. And if they are on the line, we call them semimetals. We use names like that because they tend to have properties that are similar between metals and nonmetals. All right, so if someone asked you, are the bulk of the elements metals or nonmetals, what are you going to say? Metals. Most of the elements are metals, yes. The last thing I wanted to point out on this table is the color coding on things. You may notice that certain elements are different colors. It turns out that most of them are solids at room temperature. These are all the black symbols. There are 2 of them that are blue, meaning that they're liquid at room temperature. Mercury and bromine. Yes, mercury and bromine are the 2 blue ones. It might be kind of hard to see, but they are in blue. That means that if you have mercury or bromine in their elemental form at room temperature, it's going to be a liquid, where all this other stuff will be a solid. And then lastly, the red ones are the gases. So they would be a gas at room temperature. So we have hydrogen, and then a big chunk of the nonmetals tend to be gases there.